Streaming. There we go. Somewhere on here I'll find the right buttons. All right. Are we all here though? 1, 2, 3, 4, 5. I feel like I'm supposed to have more. I am supposed to have more. This is yellow group. I should have a lot more. Where did they all go? We're 2 minutes over, and they're still not here. All right. Angel's here, Leo's here. We've got Jocelyn and Marichelle. And that's Litzy in the corner. Yep. All right, I guess that's it. Well, they can catch it on YouTube then. So, good afternoon, everybody. Once again, the system, the thing is not cooperating. I don't know. I updated drivers. I changed settings. I thought I had it, and then all of a sudden it got worse. So if you need the visual aid, which today is a pretty visual class, go ahead and join the Zoom call. And similarly, those on Zoom, I have no sound, so you have to use the chat in order to respond and ask questions. All right. But today is a super awesome day because we get to see some of the best geometry stuff, in my opinion. We get to deal with these wonderful things, 3-dimensional shapes. It's going to be awesome, okay? And we're not going to get into all the nitty-gritty. The details will come later. We're just going to hit the highlights, get some of the basic terms out of the way today, as well as practice drawing said things. So you're going to be pushing your spatial reasoning a little bit. And then we'll hit it again later this quarter, talking about area and volume. So we'll relap those. And then next semester, we'll spend the whole 4th quarter about 3-dimensional geometry. Okay, so we really get to dive into all the fun, unique things we can do with this stuff. But we got to start somewhere. And before we can begin with that, let's review yesterday's work real quick. Make sure we're all on the same page for quadrilaterals and circles. So take out your old work and check compared to mine. Again, some of these, like 1, 2, 3, 5, and 6, we basically finished. It's just a matter of lettering them. They could go pretty much anywhere in any order there, as long as make sure H is on one of the small angle corners. Make sure K is on the larger ones, and I and E are right next to it. So that one's actually pretty set. 6 had the extra stipulation with the perimeter, so you will need to label the length of these sides. You don't need to do all 4. We know the opposite sides are congruent. So if we need 2 A's, give us an A there. We need 4 B's, so one side has to give us 2 of them, and then you get the other side, add them all together, you would get that. And then the trapezoid, oh, this one was a sneaky one. And I may have led you astray a bit. I apologize for that. Because it turns out we do not want to leave our trapezoid with the actual right angle in one of the trapezoid vertices itself. I noticed, hey, perpendicular, we've got a right angle involved. But that right angle cannot be part of the actual trapezoid. Based on the information here, there's only one way to do this. You need to have the TR and the AP on opposite sides. And you need to have P, E, and A collinear. That's the key part here. They have to be all on one line. I know that A and P have to be vertices of my trapezoid because they're in part of its name. So E's got to be in the middle there. There's no other way. I mean, you could theoretically put it anywhere along here. You can stretch these out and make them longer or shorter if you want. But it has to be there, which means my perpendicular line to RE is not part of the trapezoid. It ends up inside the trapezoid. Okay? This is part of why we began with the deductive reasoning, is so that you could think through. You'd have the tools to work your way through these types of things. If I know this piece of information, therefore it must follow this next piece. It has to be that way. Okay. And then down here, we were naming some figures from this grid. There's several ways to answer some of these. The square, there's only one square in the shape. That has to be this one right here. You could name it different ways. The order here, you could start with FCAD. You could go the other way, FDAC. That doesn't matter, but you have to have those 4 letters. Okay, parallelogram. Lots of things on here qualify for parallelograms. The square is a parallelogram. This small rectangle up here is what I used. That's a parallelogram. This big rectangle here is a parallelogram. This diamond shape here in the middle, also a parallelogram. Any of those would work. In fact, that one is the rhombus. So I used that for my rhombus, JFBD. Again, as long as you have these 4 letters in some sort of cyclical order, you could go backwards, you could start it, end at any point. That's the rhombus. A square, special kind of rhombus. So you could have used this as your answer for rhombus and square. You can repeat them, that's okay. The kite is here with point H. That is the one that's uniquely a kite. However, once again, you could reuse the rhombus answer as your kite. A rhombus does qualify for a kite. Remember, we said a kite is defined as having 2 pairs of adjacent congruent sides. These are adjacent sides, they're congruent. These are adjacent sides and they're congruent. That's 2 pairs. The fact that they're also all equal to each other and parallel doesn't change that fact. It qualifies as a kite. It counts. So a rhombus is a parallelogram kite. It's kind of neat. All right, any remaining questions on that page? No? Then let's go to the next page, cycles. All right, find the measure of the arcs. 48 degrees we already had, that one was given to us. PR is over here. So if we know the whole half circle was 180, we could take 180 minus the 48, and the leftovers would give us PR, 132 degrees. Similarly, PQR, the measure of arc PQR, so P to Q to R. When they've got 3 letters there, that means you must go through all 3 letters in that order. Otherwise, you'd be on this side. It's to differentiate this route from P to R versus that route. It's the shortcut versus the long way around. Okay? And this way would be 180 from P to Q plus 48. All right? To get 228 degrees. Or, since we already calculated this one, you know this is the other part of the circle. You could do 360 minus 132. And then number 4, QPR, this way outside. So it's everything except the little slice there. So that would be 360 minus 48 to get 312. Okay, 5 and 6, I basically finished in class. There was nothing else to add to those. And then number 7, if you took the x values here, -2 and +3, and found the difference between them, that distance is 5, so the radius of our circle is 5. So we're going to add and subtract 5 to the y value, get 3, 7, and 3, -3. And add it to the x value here to get 8, 2. There's our 3 points on the circle. Any questions on the circles page? All right, then let's dive into the 3D shapes for today. We are starting with 4 basic 3-dimensional shapes: the prism, pyramid, cylinder, and cone. And to differentiate the features between them, I'm going to set up a little bit of a chart here. So go ahead and create this in your notes if you don't have something similar already. You already did the notes this week. Maybe you forethought and said, hey, I could like compare and contrast these. I should make a little table here. Tables are wonderful, great for organizing information. So we're going to make one here. Now, I wish I had like a slightly higher shelf so you could really see all these. But I've got examples here, and I bet I could hand these to any one of you, and you could sort them out pretty good into the prisms and the pyramids and the cylinders and cones. So let's start at the end, the easiest ones, right? The cone, right? Looks like this. It's the thing you put your ice cream in, okay? Or party hats, right? Nice basic shape. Cylinder, good old soup can, right? Or can of beans, right? Or drinking glass, right? With lots of examples of these all around. Step up from that, pyramid. These are the most pointy things imaginable, okay? The Egyptians are famous for them, all right? You can usually recognize a pyramid by the big point on the top, but we've got actually different kinds because the base can change, and I'll get to that in a moment. Here's another kind of pyramid, all right? And actually, you know what? I should go to bigger camera mode while I'm just showing these off. And then we have the prisms here. And so here's an example of a couple different kinds of prisms. We've got a pentagonal prism. Can you guess why it's called that? Versus the triangular prism right here. Okay? So what differentiates these shapes? What sets the prisms apart from the pyramids? And what differentiates each type of prism from another? It's all in the bases. It's all about that base. So, a prism is defined as having 2, why is my pen so small? There we go. 2 congruent polygon bases. And in fact, I'm going to add one more symbol in here. 2 congruent parallel polygons. Okay? So when this triangular prism has one triangle here, one triangle immediately opposite, they are parallel to each other. Okay? These 2 triangles, those planes do not intersect at all. They will always stay opposite. They will never cross. They're not leaning in towards one another at all. Perfectly parallel. And perfectly exactly the same. This triangle is the exact same size and shape as this triangle. If you were to make one of the triangles bigger or smaller, you'd end up with this slanty kind of prism that more resembles almost like a funnel sort of shape. And that's not what we're going for here. All right? To be a true prism, they have to be exactly the same. And then the sides, quote unquote, I put that in quotes because, well, sides is going to make a lot less sense when we get to cone. But the other sides, if here are the bases, these other sides, every time, are going to be all rectangles here. Okay? All rectangles in the prisms. So, 2 congruent parallel polygons for our bases. And rectangles for the sides. And all of those rectangles in a regular prism will be the same size, but it doesn't have to be a regular shape. Okay, this doesn't need to be a perfectly regular pentagon. So you get rectangles of different widths, but that's beyond the basics here. And if you were to draw one of these guys. There's actually a few techniques that make it pretty simple to draw, but I want to know, let's see, I need like a new pole here. What shape you would like for me to use as my base? We could make a triangle, square, pentagon, or hexagon. And I will share a poll here in the chat. So go ahead and vote. Which one would you like to see me draw for our notes here? The same principles are going to apply. So just pick one shape. And I'll use that one for the example. Got 2 votes in. It's a perfect tie. Now it's a 3-way tie. Oh no. I need another vote. It's a 3-way tie. Put this, ooh, hey, I could, if you're watching on YouTube, in the live stream, there's a link in the chat. You could vote there as well. That was a 4-way tie. I've got 4 votes, 1 for each shape. Okay, next one's going to decide it because we got to go on. I'm going to go back to blue here. Oh, hexagon takes the win. Okay. So thank you very much. We'll go for a hexagon. Of course, you picked the most complicated one. All right, so key factors. 2 perfectly the same congruent bases and connected by a bunch of rectangles. So I'm going to start with drawing my hexagon. And I'm going to try to make it fairly regular-ish. Doesn't have to be. There, and there. And then what you want to do is draw a second one of those somewhere up and to the right of that guy. And the closer you can make it to being exactly the same, the better the effect will be. Hey, that turned out pretty nice, I'd say. And how far you place it compared to the original will determine how big or small, how short or long your prism will be. Because then all we have to do is connect all of the corresponding corners or vertices, right? And this one goes back to there. Nice. This one to there. Now we see it start to take shape in your mind there. All right, that's it. 3D drawing with Mr. Apple. I should start an art class. Okay? Now, if you really want to get the effect popping, what we should do is go back and make some of these actually into dashed lines, all of those that we would not see. So I'm creating this view where you're looking in and you see the front of it, you see kind of one of the sides, but you don't really see these back portions here. There's some edges that you won't see if this was an actual solid piece. So I'm going to go ahead and I'm going to erase little bits of those. And that would be gone, that would be gone. Right, so you wouldn't see that one, you wouldn't see this one. And it's really hard because it's right next to the other line that I would see. And you wouldn't see these sides of the back hexagon either. Now if I zoom back out, it should go a little bit better. You retrace this line. A little better, right? There you go. Three-dimensional hexagonal prism. That's actually fairly easy, right? Because it doesn't matter. You didn't need to make this regular. As long as you can duplicate whatever shape you drew the second time, connect them with a bunch of straight lines, and you're set. Okay. Let's go on then to the pyramids. Pyramids are even simpler than prisms because a pyramid only has the... Whoops. We lost the stream temporarily. Are we back up? Okay, and we're back. Good. So pyramids has the one base on the bottom, so it doesn't need to be congruent to anything. So a single one polygon as a base, and the sides of the pyramid are all going to be, you can see from my examples here, triangles, right? And once again, if the base is a regular shape, then all the triangles will be congruent, but they don't have to be. So we get one polygon base and triangles, 4 sides. Okay? Drawing it is going to be fairly easy, except we got to do one thing. If you want to draw a pyramid looking like it's sitting there on the desk, and you're looking down at it like this view, then what you see as the base is not, as it views to you, a perfect square, right? Your image there, your view of that square is not as perfect as a square as if I hold it like this, right? It doesn't look like a square. It's a little slanted, okay? So we got to draw our base shape with a bit of a slant to it. So I'm going to do that now. I'm still going to go for the hexagon to match my prism there, but I don't want to make it quite the same. I want to squash it flat. This goes back there, and then back here, and then stretch over there, and then out like this. See how it's kind of skewed a little bit? And it ends up looking a little funny for now, but it'll turn out okay once I get the rest of the pyramid in. Now, all we got to do is pick a point above that. You can pick right there if you want a nice short pyramid. You can go way up here if you want a big tall pyramid. That is up to you. But pick a point up there and then connect that point to, with a straight line, please. I said straight line, please. Thank you. To every vertex on your, in this case, hexagon. And there it comes together. All right. Now, once again, we can, I'm going to make this a little bit bigger. It'll be easier to work with. We can give this a slightly better effect if we make the hidden so-called edges into dashed lines instead. So I wouldn't be able to see that guy, and I wouldn't be able to see that guy. Would disappear as well. So those should be dotted lines because they would be tucked behind the base of the pyramid from that view. There you have a hexagonal pyramid. And we give this tippy top a special name. All of the corners, if you will, of a 3D shape are properly known as vertices, or single a vertex. Just like on a polygon, right? The corners are actually called the vertices. But on the pyramid, one of those vertices is unique and different from all the rest. It's the one where all the triangles meet. It's the tip-top point, that gold cap that goes on the one in Egypt. And so we give that the special name of the vertex. Everybody else is just a vertex. This is the vertex. It's the most important one. So important that we give it a the, but we didn't give it a unique name. That's okay. Mathematicians are lazy that way. All right, and now all we've got left is the cylinder and the cone, and those are just circular versions of the prism and pyramid. So our bases are going to be very similar. For a cylinder, we need two congruent circles now, and oops, still parallel. Two congruent parallel circles. And our side is actually a single rectangle. Just one, no S. Because it's a one fluid face, right? There's no edges to distinguish separate sides. I want you to imagine taking the label off of a soup can, and you unroll that, and you get one long rectangle that would wrap all the way around. So one single rectangle creates the side there. And when we're drawing it, we're going to kind of combine tactics here. Because we could still go with the two circles and connect those like that and call that a cylinder. That will work. But I'm going to go for something a little different. Where's that thing? I'm going to use that slant method. And I'm going to give a slanted circle, just like that, right? It's really an ellipse. Because when you look at it, not from straight on, but when you look at it from an angle, you get an elliptical shape. So draw an ellipse, and then drop each side straight down from there. And you can make those sides as long and tall as you like, two straight sides, and then draw a matching ellipse at the bottom. Or you could go backwards. You could start with the bottom one, draw two straight lines up, and put one on the top. Or you can draw both your ellipses and then connect them with the lines. I think going ellipse, two lines, then ellipse, helps you make sure the ellipses stay lined up. And then for our final effect, we get to see the entire top of the cylinder, but we can't see the back edge of that can. So we're going to make that half of our ellipse into a dashed line. And now we've got a can of beans sitting on a table right there. That's our cylinder. All right, let's wrap this up. A cone, you could probably guess by now, is one circle for the base. We have that guy right there. Like the cylinder, we really only have the one single side, but it's not immediately obvious what kind of shape that is. If we were to wrap the cone, right? If you bought like a conic, take a paper hat, right? A party hat, and you were to unfold it into a flat piece of cardboard, that shape would end up being a proper name is a sector. It's a large slice of pizza. So we'll talk about this in a moment. The net of a cylinder, if we have our circular base here, the other part of it would unfold into something like this, okay? This right here is a sector. It's a big pizza wedge, okay? And it's going to be a lot wider than you might expect, right? If the cone is only this wide, if you unravel that, it's going to end up, almost 3 times as wide. Specifically, just a little bit more than 3, actually. Find out why later. There's a secret number there. And drawing the cone, we'll just combine all of our effects so far. One slanty circle that's actually an ellipse. Just like the pyramid, pick a point centered right above. And we only have to connect, not in a curve. I got to turn that off sometime. We only have to connect the outside edges and turn that back edge into a dashed line. Nope, too far. Here we go. There's our cone. All right, any questions on these 3D shapes? Okay, so in answering the remainder of these questions for today, first two just ask you to draw two of them. Right? We practiced doing that. 3 and 4 ask about the net. What is the net? The net is what happens if you were to unfold the shape. Or, working the other way, it is a scrap of paper that if I was to cut this shape out and fold along all of the edges, it would come together and form a what? That's what they're asking for. What would this thing be if I were to combine it here? This is a big test of your mental ability to visually manipulate objects. Okay? Your spatial reasoning will really be put to the test if you try to visualize what's going on here. To help you, I do have some computer animations here. If you just Google search for geometry nets, you can find some really cool ones. Right? Look at that guy, just folding and unfolding there automatically. Will it play again? Yeah, there it goes. Right? That's what we mean by a net. We're going to take this flat shape and fold it up to form all 6 sides, in this case, of a cube. All right? That's what a net does. Now, we can use the properties we talked about that distinguish one shape from the other to identify what shape it's going to have to be, even if you struggle with the actual visualization. If you can't see the shape that it's going to become in your mind, that's okay. Use the process of elimination. Are there 2 identical polygons in the net? Or is there only one unique polygon and the rest are triangles? Okay. Are there any circles involved? If there's one circle, it's got to be a cone, almost certainly. If there's 2 circles in a rectangle, it's going to be a cylinder, right? If it's 2 polygons and a bunch of rectangles, it's going to be some kind of prism. Which kind of prism? Find the shape that's not a rectangle, and that would be your base of your prism, okay? So you can use that basic information to identify both of these nets, even if you couldn't actually see the 3D formation. And then, after you know what it's supposed to be, use our drawing techniques to sketch it up there. All right, and I came across a site earlier that has some manipulatives where you can actually drag a little slider and see in real time some nets forming and unforming. Let me go ahead and repost that to your guys' class here. Nets demo. There we go. Okay, so I just posted that on Google Classroom. You can play with that as well. The next set of exercises, 5 and 6, talking about slicing and dicing. If we were to chop through this shape, what shape would be revealed inside? Okay, think about cutting open an apple or an orange or some kind of fruit. It starts roughly spherical, and then you cut it in half, and now you have a flat circular face. Okay? So what shape is left if I was to slice my cylinder this way? What shape do I get if I slice a cone this way? Okay. Imagine you were making a stamp out of it. You cut it in half and then stuck it in paint and stuck it on paper. What stamped shape would you make? 7 is a prism made out of smaller cubes. If you have a Rubik's Cube, right, this is basically a slightly larger example of one of those. It's one cube made out of a bunch of smaller cubes. What you need to do is figure out how many cubes are not shown. So take a look at this cube here. If I hold it this way, right, you can see this face, the top, and these two front sides. What you don't see immediately is the back and these two sides, the ones that my fingers are actually holding on to. Okay? So that's what the picture we have here. We've got three of the faces showing. There's three sides to that prism that you can't see. They want to know how many little cubes are in there that you can't see at all. Be careful. The ones on the edge, you can see that top face, but you don't see the back side of that cube, but you do still see the cube here. So don't count just these squares on this face, because some of them are already used. So you're going to have to figure that out. If you have a Rubik's Cube at home, pick that up and practice with that and work on it. Okay, if I hold it here, I've got this many cubes, then you can turn around and say, how many do I have left there? Use that information to expand to answer question 7. And then question 8 deals with the lengths of a three-dimensional shape. If you understand that three-dimensional object, you will know that the height of the object is constant. Okay? It doesn't change. The height of my cube on the left side is still the height of the cube if I measured on the right side. That doesn't change. So if this side is 4 units high, this side must also be 4 units high. That's the same height of the same object. There's a secret back edge that you can't see there because it's solid that's 4 units high. This front side, from here all the way down to the bottom, 4 units high. Any distance from the very bottom to the very top must be 4 units high along any plane. So use that information to be able to add and subtract and work out what the missing measurements x and y must be. You will use all of these numbers. Okay. I think I've set up each one. Are there any remaining questions? No? Then you have the remaining 6 minutes to work. I'll leave you to it.